So now let's solve the subject test that we have for linear algebra. Let's solve these problems. And while we are solving these problems, one of the often asked questions, right? This is a question that many of our students have asked us, which is that I understand all of the theory. I also understand all of the solved problems that you have solved as part of the course videos. But when it comes to practice problems, right? We seem to be lacking when we try to solve these problems, right? And that's very common. To be honest with you, this is a very, very common problem that many students have in the early stages of their practice, right? And it's only through practice and a few tricks that I'll discuss as part of these solutions, which will help you solve these problems better, right? Especially mathematical subjects like linear algebra, probability, statistics, calculus, discrete mathematics, etc., right? For these subjects, again, remember that some of the questions in this practice test are slightly above the gate level, and that's by design. We want you to be prepared for the worst case, right? We want you to be prepared for the worst case, for the toughest of questions that have ever been asked in gate or that could ever be asked in the near future based on the past data, right? Again, it's very, very understandable that you're not able to crack some of the practice problems, not all, but certainly some of the practice problems. So when I solve each of these problems, I'll also try to shed light. I'll also try to shed light on how to solve a problem, not just the solution itself, but on the approach on how to solve a problem, right? I'll try to shed some light on this. Again, this is not going to be perfect. I'll also try to shed some light on how I personally think, how I tackle a problem, how I personally tackle a problem myself for many of these linear algebraic problems here, right? And these are general lessons, especially for mathematical topics. Okay, hope this will help you get some more confidence, and it will also help you solve some of these problems better in the future. Okay, so let's go step by step. So again, we have 25 questions here. And I also have detailed solutions for each of the questions written in text. This document is already shared with you. As soon as you finish taking the test, you get each of these questions and detailed answers, right? So I've written the answer, I've pre-recorded or pre-written the answers and questions so that it will save us some time, because we have 25 questions to solve and not 10 or 15 questions that we typically solve over a 90-minute period, right? So since we have more questions, I don't want to spend time writing the question or writing the answer in detail. That's why I'm using this type of format today. Okay, so let's go through this first question. Okay, so the first question is this. I'll also tell you how to tackle this question, or how I personally tackle this question, right? So we have this thing which says f of x equals to determinant of this matrix, and it says f of 100 is equal to, and we're given 4 options. Okay, look at this. Most of these options 0, 1, 100, minus 100, right? If you look at it, if I place 100 here, this will become 200. This will become 100 multiplied by 99. So this becomes a fairly complex 3 by 3 matrix, for which computing the determinant is going to be non-trivial, right? I mean, if you have to manually compute the determinant, it's going to be hard, right? Which means, and remember, when the person who set this question gave this question, he doesn't want you to manually solve it, okay? Because if you just plug in these numbers, right? If you just plug in these numbers here, this will be very tedious to solve manually. Hence, you should always think of it from the perspective of the person who has set this question. And if you look at the options 0, 1, 100, minus 100, there must be some shortcut to solve this problem. Okay, this is how I think. Okay, I'm trying to shed light on how my thinking process works out. Because of the 4 options given and because of the tediousness in solving this question manually, there must be some shortcut that we have to employ, right? Or some property of determinants that we have to employ. And the moment you look at determinants like this, the first property that should strike is elementary row and column operations, right? This is the first thing. By performing a bunch of elementary row and column operations, we know how the determinant changes. Or through some row and column operations, the determinant does not change at all, right? And the moment I think of elementary row and column operation, the other thing, so this is a very important property in computing determinants efficiently. Okay, and this is something that we have studied in the course. So I'm employing this tool right now. To solve this problem, I've made a couple of observations and I'm now looking at all the properties. Okay, again, most of mathematical problem solving is about leveraging the properties and solving problems like this. Again, these problems are not going to be very hard, because the examiner, the person who has set this question, expects you to solve it in 2 minutes to maximum 5 minutes, under 5 minutes, right? Hence, it should not be very complex, right? So whenever you see a problem like this, row and column operation should come to your mind. And look at this here. Should you take row operations or column operations? I would say column operations. That's because if I sum up these two, look at this. If I sum up these two, it is becoming column 3, right? So what if I make column 3 equals to column 3 minus column 2 plus column 1? Okay, because then this will become 0. Look at this. See, if I can make all 3 of them 0, then the determinant will be 0. Right? If one column or one row of a matrix is 0, the determinant is going to be 0. So I'll try to see if I can make this 0. And remember, if I make this 0 when I'm computing the determinant, I don't have to multiply these two. Right? So imagine if I'm manually computing the determinant also. Right? If I can somehow make this equal to 0. And how can I make this equal to 0? If I say column 2 plus column 1 minus, so column 3 equals to column 3 minus column 2 plus column 1. Okay? These are two operations now. This is one operation, and column 3 minus column 2 plus column 1 is the second operation. But by performing this elementary column operations, my determinant doesn't change. Okay, so now when I employ this, what happens now? So this will become 0. What about this? What is this? This is x square minus x, right? What is this? So this is x square minus x. When I add 2x to it, what happens? This will become plus 2x. Which means this is x square plus x. And what is this? This is also x square plus x. Right? Which means this will also become 0. Now look at this. Now the third part which is left is this. Right? If you look at this term, again, you can manually verify very easily. See, if I take x minus 1 out, if I add these two, imagine if I'm adding these two, what will I do? I'll take x minus 1 out. Right? I'll take, because that's common between both of them. I have 3x on one side. Right? Plus, what is there on the other side? X into x minus 2. This is what I have, right? Now here also I have x minus 1. So now I need to see if this is equal to x plus 1 into x. So if I simplify this, what happens? If I simplify just this internal term here, this is x square minus 2x plus 3x, right? Which is same as x square plus x, which is what you're getting here, right? So very simply, I can also show that this plus this is equal to this. Which means by performing this simple operation of column 3 equals to column 3 minus column 2 plus column 1, this whole column becomes 0, which means the determinant becomes 0. Right? So very quick way of solving it. Okay, so the answer here is A, where f of 100 equals to 0, because for any value of 100, this determinant equals to 0, irrespective of it being 100 or not. Okay, the key takeaway is this. The key takeaway here is, by looking at the options and by looking at the number being very large, you have to recognize that you can't solve it manually because it's too tedious, and the examiner, the person who has set this question paper, wants you to solve it in 2 to 5 minutes. Hence, there must be some other properties that we can employ, like row and column operations. As soon as you think of row and column operations, I thought of column operations because summing these two things will sum into this. Again, part of it is the trick of recognizing that I have to use some basic properties of determinants. Part of it comes with practice. Okay, by just looking at this matrix, within a couple of seconds, I recognize that I have to add these two and subtract it from C3 to make this 0. And that comes with a little bit of practice, but I hope you got a sense of how I think when I have to solve a problem like this. Okay, again, the detailed solution is here. Okay, the detailed solution goes in steps. First, it will make C1 equals to C1 plus C2. Then, if you notice, this column and this column are same, because these two columns are same. Right? These column vectors are linearly dependent. Hence the determinant equals to 0. This is another way to argue. Okay, sounds good. Now let's go to question 2. Okay, again, this is a very simple question. If you look at this question, the first thing that is asked here is, you're given a matrix P which looks like this. You're given a matrix A which looks like this, and it's given that Q equals to P into A into P transpose. Very good. Then it says x is equal to this, okay, where q is raised to a very large exponent, right, where q is raised to a very large exponent here. Then what is the value of x, or in other words, what is the value of this? The moment you see this, first thing you recognize is that A and P are 2 by 2 matrices. Probably when the examiner set this question, these 2 by 2 matrices are very simple to compute inverses of and transposes of. It's very easy to multiply 2 by 2 matrices, right? Instead of 2 by 2 matrices, if these were 3 by 3 matrices, it would take more time, right? So first thing is, because these are 2 by 2 matrices, we can do some simple, I can multiply P with P transpose, for example. Okay, I can do some of those things, right? And see this, he's giving that Q equals to this, and he wants you to compute P transpose Q into P. This is what they want you to compute, okay? First thing, as soon as this is done, let's actually write it down. What is this now? Okay, what is this? This is P transpose. Let's take what is Q? Okay, let's look at this. Because all these are 2 by 2 matrices, it should be easy to solve some of this. Okay, so the moment I see this question, I think, okay, what is Q square now? Okay, because I need to compute Q power 2019. What is Q square first? Let's actually look it up. Q square is PA P transpose multiplied by PA P transpose. Okay, now I have this P transpose into P. Okay, and what if P transpose is same as P inverse? Then these both will cancel out. Okay, is P transpose and P inverse the same thing? If I multiply P with P transpose, what happens? Look at this. This is my P. If I make P into P transpose, okay, I can manually check it very, very quickly, right? I can actually manually check it very, very quickly. This is my P. What is P transpose? P transpose is this, right? P transpose is this. Now if you look at this, this multiplied by this, so this into this is 3 by 4, this into this is 1 by 4. If I sum them, I'll get 1. What about this into this? It will become 0. So because it's a 2 cross 2 matrix, you can verify that this is equal to identity matrix, which is 2 cross 2. You can very quickly, within a few seconds, you can verify this, right? Which means P into P, which means P transpose is same as P inverse. Okay, because P transpose is same as P inverse, these two, when you multiply them, this will become P into A square into P transpose. Okay, because this was there, because I want to cancel these two out, I checked whether P transpose is same as P inverse. And the way this matrix was constructed, because this is a 2 cross 2 matrix, even the examiner would have thought about this as a 2 cross 2 matrix and thought, okay, now I can solve this easily. Because it's a 2 cross 2 matrix, I can very easily verify that it's actually an identity matrix, concluding that P transpose equals to P inverse. Okay, this is what I have. Now what about P cube? What about P cube? Using similar concept, again, doing the same process again and again, I can show that P cube is also equal to P A cube P transpose. I can easily say this. And look at this. A is a very simple matrix. I can compute A square A cube very quickly. Okay, this is another way. See, the way the matrix A has been asked in the question is very simple matrix. I can compute. See, if this is my A, right? A square is very, very simple to compute. A cube, so on and so forth. Now what do we want to compute? We want to compute Q power. So because of this logic, I can write Q power 2019 as P into A power 2019 multiplied by P transpose. Again, always think about it from the examination or the person who set this question, from the examiner's perspective. Now I know, see, look at this, this is Q power 2019. What is the question that is asked? What is X now? X is P transpose into this. P transpose into P into 2019 into P transpose into P. Right? That's what X is, right? And the question here is, what is X? Now this P transpose and P and this P transpose and P also will cancel out. So X will be equal to A power 2019. See, all this worked out very easily by just simply recognizing that P transpose equals to P inverse. And why did I have this hunch to start with? Why did I think this might be true? And why did I even check for this? Because I had this expression. I thought if P transpose is same as P inverse, these two could cancel out. That's how I got this idea or the hunch. Okay. Now, since X is nothing but A power 2019, I'll start computing what is A square, A cube, so on and so forth. Okay. Again, we have listed all of that here below in the answer. Right. So if this is A, this is what A square is going to look like. Similarly, by just going through the same logic, A power 2019 is going to be 1, 2019 0 and 1. Right? And where is that answer? That answer is option A. Right? So the key observation is that this is a very easy matrix to raise to the power, and this matrix transpose is its own inverse. Okay, for this matrix, P transpose is P inverse. This is one key observation, and the second key observation has been that a power k is very, very simple to compute. It is nothing but 1, k, 0 and 1. Once you have this, it's just simple algebra and you've solved all of the problems. So this is also not a very hard problem from a problem solving standpoint. Okay, so let's go through the third question now. So what does it ask? It says, again, this is a very simple problem. Okay, relatively speaking. A is a 3 cross 3 non-singular matrix. What is a non-singular matrix? Which means A inverse exists. What does a non-singular matrix mean? Means det of A is not equal to 0, or in other words, A inverse exists. Right? That's what a non-singular matrix means. And it says A into A transpose is A transpose into A. And B is given as A inverse into A transpose. Then what is the value of B into B transpose? This is again simple algebra. B into B transpose is what we want to compute. Okay, what is B? B is A inverse into A transpose. Okay, this is B. What is B transpose? B transpose is A inverse into A transpose transpose. Right? Now how will we simplify this? This will be A inverse into A transpose. Now we know that AB transpose, again this is a simple property of transpose, right? AB transpose is B transpose A transpose. We have already studied this. So A transpose transpose is going to be A itself, right? A transpose transpose is going to be A itself. A inverse transpose is going to be A inverse transpose. Okay, very simple. Till here everything is good. Now A transpose A. Now look at this. It says, look at this. It says A into A transpose is same as A transpose A. Now look at this. Here, if I change this order, look at this. If I change this order, I can cancel out A inverse and A. Similarly, I can cancel out A transpose and A inverse transpose also, right? And here, that's why this rule has been given. Remember that this, so when the examiner set this question, he gave this reasoning, he gave this equation for us to swap these two. Because A transpose A is same as A transpose, I can write this as this multiplied by A transpose into A inverse transpose. Okay, this is equal to I and this is also equal to I. Right? So since both of them are equal to I, my option C is the right option here. Again, it's a very, very simple problem. You just have to simplify it, and again, when you're simplifying it, keep a lookout for all these options. Okay, when you're simplifying this, try to get your solution into either B inverse format or B inverse transpose or I plus B. See, as soon as I recognized this, I said, and as soon as I observed this given statement, I said, okay, if I can move these two around here, I can make this identity and I can also make this identity, which means option C could be correct. And given that I have this, which I am just using here, again, this is a straightforward problem where you're applying simple rules here. Nothing very fancy. Okay, this doesn't require big leaps of understanding. This is simple algebra. This is like simple algebra in which you'll become better as you solve more and more problems through the rest of the through the rest of your preparation. Okay, so don't worry about it. So these problems should be easier and you should be able to solve them, truth be told. Okay, now let's look at this question. The number of values of k for which the system of equations has infinitely many solutions. Okay, first of all, again, you have to understand what does it mean to have infinitely many solutions. Look at this. These are two equations and two variables. There are only two variables here, right? And k is what we want to determine it to be, right? We want to determine what k is, and you have basically these are 2D equations. I can think of them as lines, right? I can think of this as a line and I can think of this also as a line. And if these two equations of lines, right, have infinitely many solutions, what does that mean? It means both these lines are fully overlapping on one another, right? These lines have to be overlapping on one another. For these lines to be overlapping on one another, the ratio of this to this, right? Look at this. If I have 2x plus 3y equals to 4 as one line, then for us to represent the same line, I can multiply both sides by the same constant. If I multiply both sides by the same constant, They both are representing the same line, right? Right? That's what it means to have two lines which are fully overlapping, right? Which means what? Which means the ratio of 2 by 4 to 3 by 6 to 4 by 8 is the same. So here also, for these to have infinitely many solutions, these two lines should be fully overlapping, as we have discussed in the geometric interpretation of system of equations, right? For both these lines to be overlapping, this k minus 1 by k, this ratio should be same as 8 by k by 3, should be same as 4k by 3k minus 1, right? Now look at, now we are given 4 options, right? We don't even want to solve this. So if I place in 0 here, what happens? Okay, division by 0 is not valid. Okay, so this won't work out. If I place 1 here, what happens? 2 by 1, so this is equal to 2. 8 by 4, because k equals to 1, that's 2. This is 4 by 3 minus 2 is, so 3 minus 1 is 2. 4 by 2 is 2. So this whole thing, all these equations are valid when k equals to 1. Because we are given 4 options, and it's very easy to place these options into this. Right? I can just insert 0 here, 1 here, 2 here, and that's it, I'm done. Right? Very, very simple problem. The key observation here is, for two lines to be fully overlapping, right, these ratios of coefficients should exactly be the same. That's all is the observation here. Otherwise, it's a straightforward problem. Okay? I hope this gave you a good understanding of how to tackle this problem. Now let's go to question 5. Okay? So, okay, this is a slightly tricky problem, because here I'm assuming that you know the cube roots of unity. Again, this is a concept that you probably have learnt in your 11th and 12th class, right? I'm assuming that you have learned this concept in your 11th and 12th class, right? So if you have, again, the key observation here is, if you want cube roots of 1, again, if you have forgotten the concept of cube roots of unity, it's perfectly okay to go back, revise that concept and tackle this problem. Okay, there are 3 cube roots of unity, 1, omega and omega square. Okay, these are the 3 cube roots of unity. Again, this is something that we've learnt in our, again, here omega and omega square are complex numbers. Okay, again, if you have forgotten this concept, I'm not assuming that you remember everything, right? Just type cube roots of unity. Just Google search for it. Okay, you'll get a bunch of articles. Let's pick the first article here. Look at this. It clearly says, in this article it says, x equals to 1 is 1 cube root of unity. Again, you can solve this also, right? By the way, you can solve this. So cube root of x equals to 1 is same as x cube, right? Cube root, sorry, my bad. So this, the linear equation that we'll get here is cube root of 1 equals to x, which means 1 equals to x cube, which can be written as x cube minus 1 equals to 0, right? When you have x cube minus 1, you can write this x cube minus 1 as x minus 1 into x square plus x plus 1 equals to 0, as shown here. Okay, here this should be x minus 1, right? So when you have this, what does this imply? This implies that x is 1, or take the roots of this using Sridharacharya's formula, right? Whenever you have a quadratic equation which is ax square plus bx plus c equals to 0, what does Sridharacharya's formula state? X equals to minus b plus or minus b square. Okay, look at this, plus or minus b square minus 2ac. Again, if you have forgotten Sridharacharya's formula, that's again very possible, right? So let's say quadratic. Sometimes people do forget. Okay, so quadratic equations. Again, just Google search for it. You'll get a bunch of equations. You'll get the closed form solution also. So if you have forgotten it, it's perfectly okay, right? Just for completeness, again, you have b square minus 4ac by 2a. I just stopped it in between because in case you have forgotten it, it's okay. Just try to recall this. Okay, some of these equations are important to remember when you have to solve equations like this, right? Again, going back to our, again, it's okay. In mathematics, sometimes we all forget it. It's perfectly okay. But the key observation here is omega square and 1 are the cube roots of unity. Okay, actually I've forgotten the exact values of omega and omega square. Okay, again, for that you can always refer here. This is your omega, this is your omega square, and this is 1. If you notice, omega and omega square are just, there is only this minus symbol difference. So when you make this plus symbol as minus symbol, you get omega square. Okay, again, if you've forgotten, all of this is also alright. All you have to remember is that 1 omega and omega square are cube roots of unity. If you remember that, this is perfectly okay. And we have not seen questions like this in previous year gate problems, but we still thought, why not do it? Because this is a slightly tricky problem, let's solve it. Okay, so what does it say? It says omega not equal to 1 is a cube root of unity. And let S be the set of all non-singular matrices. All non-singular, what is a non-singular matrix? Non-singular matrix basically means det of A is not equal to 0, right? So let S be a set of all non-singular matrices of this form, okay, where each of A, B, C can either be omega or omega square. The number of distinct matrices in set S. See, first of all, this det has to be not equal to 0. For it to be not equal to 0, let's actually compute the det of this, right? Again, let's look at the solution step by step, how to solve this question. See, at the end of the day, it all boils down to how many values can you give for A, B, C such that this det is not equal to 0, given that omega, omega square and 1 are cube roots of unity. That's all it boils down to. Okay. Again, very, very simple question. Now let's see see, because it's a non-singular matrix, right? Let's actually compute the whole det of this. Det of this is going to be 1 into 1. See, 1 into 1 is going to be 1. Again, if you simplify this det, this is what you will get. Just manually do it, right? 1 into 1 minus c omega. So you get minus c omega term here. Then a into omega. So you get a minus 1 into a omega term you got here. Again, there is omega square plus omega square, right? You got that term also. Sorry, not omega square. Omega square into c is the term that you have. Then when you have b, omega square minus omega square, it will become 0. So what it's literally saying here is that this term is not equal to 0. Okay, now comes the fun part. Okay, look at this. This is where the mathematical tricks or the mathematical ingenuity comes into place. Till here it's straightforward, right? Because you're given that this matrix is non-singular, you have obtained this. Now for this to be non-zero, again, what do we have to compute? Look at this. The key here, the most important key here is that b. What do we want? We want our b. We want values for a, b and c. That's what we want to obtain, right? That's the core objective that we have in front of us, right? Now how do we get the values for a, in terms of a, b and c now? Right? That's the challenge here, right? Now how do we arrive at that challenge? Now since from this equation I need to express this equation in terms of a's, b's and c's. Okay, can we do that? Just in terms of a's, b's and c's. In terms of multiples of a's, b's and c's. Can we do that? Okay, that will be fun, right? Now here comes the big observation. Okay, so if you look at this, I can write this in as this. Actually, I think there is a small error in this equation. I think this should be c here, not b. Sorry, there is a small typo here. Okay, so when you simplify this equation, what you get is this. Okay, and how did we come about this? Because we have 1 here. See, we want to write it in this form so that the math becomes easy. I'll tell you why the math becomes easy in a little while. Again, the big leap here is to go from here to here. That leap is the hard one. This is easy. Coming to this equation is also easy. This leap, this step is one of the harder steps in this problem. Now, how did we arrive from here to here? Look at this, I have 1. Okay. See, I want to write it as some 1 minus. See, because I have this term as 1, I need to have 1 into 1. Right? Now, I have a omega and c omega here. Right? Now, this 1 will get multiplied with something. Right? This 1 has to get multiplied with something. Right? Look at this. I have minus a omega and minus c omega. So, if I have a omega here and c omega here, because this one would get multiplied with this and this one would get multiplied with this, I have a omega and c omega terms also. I have 1 term also. Now, when both of these two things will get multiplied, what happens? Minus minus becomes plus. We get ac omega square. Okay. So, I'm trying to write this in terms of these two terms. Now, the reason I'm trying to write it into these two terms, this is the important part, is because I don't want this value to be equal to 0. Because if I write it in this form, immediately, if this is not equal to 0, right, I can immediately write this as 1 is not equal to a omega and 1 is not equal to c omega. Because if any one of those two things are true, then this would become 0 or this would become 0, and this whole thing will become 0. Right? The whole reasoning for me to write it in this form. Again, this is the important step here, right? So from here, the reason I took this leap to represent it in this form is to be able to find what values of A, what values can be taken by A, and what values can be taken by B, and what values cannot be taken by them. Right? The moment I have these inequalities, I can immediately say, because omega is a cube root of 1, right? A cannot be. Now A cannot be omega square. Because if A is omega square into omega, look at this, omega square into omega is 1. Right? Because omega is the cube root of 1. Similarly, from this I can say, C cannot be also omega square. B can be anything. Look at this. This expression does not have B. This expression does not have B. Then B can be anything. B can be omega or omega square. Because look at this. What is the question now? Let's not forget the scope of the question. The question says, what is the size of this set? What is the size of this set where A, B, C can either be omega or omega square? So we have shown that A cannot be omega square. We have shown that C cannot be omega square. We have shown that B can be omega or omega square. So what does this imply? This implies that A can only be omega, C can only be omega, right? There is only one possible value for A, one possible value for C, but two possible values for B, which means the total number of matrices that I have is 2 into 1 into 1, which is equal to 2 matrices, which is option A, right? So in this whole problem, when I was solving this problem, the big leap that I had to make, truth be told, okay, for me to jump from this equation to this equation, this is what took the most logical time for me, okay, or I felt especially. It didn't take too much time, it took a few seconds, but for me to jump from here to here was the key insight. This was the key insight or the key step that enabled me to solve this problem. Without making this step, solving this problem would be much harder. Okay, so that's why I would say that this is the key insight. This is C again, by the way. There is a small typo here in this document. This should have been C. Okay, so I would argue that this is the key insight, and when we are able to represent this in terms of this, and again, it's very important to understand why we are trying to represent this problem into this form. The reason we are trying to do that is all because of trying to find what values. See, because the moment I have this, I can write 1 is not equal to A omega, because otherwise this expression will become 0, and 1 is not equal to C omega. To come up with these two inequations, okay, I had to express it into this form. So whenever you have equal to 0 or not equal to 0, okay, again, this is a key lesson here. Whenever you have the equal to or not equal to 0, to find valid values or invalid values, it is very important to express an expression like this into product of two expressions like this. Okay, imagine if this was equal to 0, then I can say A is equal to A, 1 equals to A omega, or 1 equals to C omega, right? In this case, this is true and this is true. Both of them have to be true, because even if one of them is equal to 0, the RHS, this inequality will not hold. Okay, again, that's the key insight step that took me a few seconds to realize.